Hello, I'm Marcus, and welcome to Lab 5. For Lab 5, I chose to model our solar system. So, I'm modeling the planet's orbit around the sun. So, in this, just to simplify things, I only used the force of the sun. So, I neglected any interplanetary forces of gravity. So, in this model, we can assume that the only force going to be acting on each planet is the force of the sun. Which, using this equation right here, we can get the magnitude of the force, which is the big G constant, the mass of the sun, the mass of whatever planet we're looking at, divided by the magnitude of the distance between the two objects squared. And using this force, we know that the direction of the force will always be pointed along r hat, negative r hat, towards the sun. And using this force, since it's the only force, we know that this force is equal to F net, and we can then thus update the velocity of each planet through this, and therefore update the position of the planets as they orbit the sun. Here's a quick snippet from the code. In this little snippet I only included Neptune, since in the real code there's all the planets and that can get kind of jumbled. Right here, as you can see, you got Neptune's mass, you've got the momentum, which is just its mass times its velocity vector, initial velocity. Right here is just a trail outlining it as it moves. Here's the gravitational constant. Inside this while loop, we're constantly updating the position vector, which is just Neptune minus sun. This gives us a vector pointing towards Neptune from the sun. And we thus take the magnitude of this, and then we can plug this into the gravitational force equation. But we're going to make it negative so that it's pointing towards the sun and not towards the planet, since the sun is the one acting on the planet. Here's just the momentum update, position update, and from this we get this image right here. As you can see, there's each of the planets. To simplify things also, I made that they all started on the x-axis, so that's why they all starting in line. I know this is not real to the real world model, but it was easier to model this way. And as of course we got the sun in the center. And here's just to prove kind of the accuracy of the model I made. We know I set the while loop for 1 Earth year, as you can see here, and we know that 1 Earth year is equal to 0.53 Mars years, and we see this actually pretty much accurate. So we've got 1 green circle, and this accounts for a little over half of a year of Mars. Here's just some of the what if questions, just kind of looking at what would happen if the mass of the sun changed by a factor of 10. Right here we see if we make the mass of the sun to the 31st and to the 30th power, we get an orbit that kind of sucks in the first 4 planets into the sun. This is just because the force of gravity is going to be stronger than the angular velocity right here, pulling it in and making it more elliptical. Here is just the regular mass of the sun, which is the model I just showed you, which is just perfect circles. And here's the mass of the sun to the 32nd power, which is so strong that it pulls in the first 4 planets and shoots them in straight beams across, just because of how great the force is. And here's if the mass of the sun was to the 29th power and lost a factor of 10. And here we see that the force on the planets by the sun is so little that it's not even going to have an orbit. So the planets are all traveling at a velocity that is above the escape speed of the sun. So their direction's changing slightly, but they're not orbiting the sun, and they're going to keep on going. Conclusions. So I think the model held up pretty well, as we saw from the Earth years compared to the Mars. But the main difference here is the orbit shape. So we know that our real orbit of Earth in our solar system is most of the planets are elliptical and not perfectly circular. And the reason this is circular orbits the forces have to exactly balance out. So in this case, since the mass of the sun was the only gravitational force acting, this helped, and also the centrifugal forces. So in my model, it means that the gravitational force was equal to the centrifugal force the entire time, giving it a perfect circular orbit. But in real life, it isn't this way. So if we wanted to further make this model more realistic, we'd have to add in, first off, the gravitational forces between planets, and that should help a lot. But thank you for watching this lab. Hope you guys have a great day.